Hello, my name is Ralph Cordiano. I'm the lab manager of the Penn State Student Space Programs Laboratory, and have acted as the project manager and systems engineer for the OASIS instrument. The entire OASIS team and I would like to thank you for the opportunity to present our work. In this talk, we will discuss the problem OASIS addresses, the background information surrounding how it does so, the system and subsystem level design of OASIS, and the testing and simulation methods used to verify this design. Path-to-flight design changes and/or tests will be discussed throughout the talk to give a clearer picture of design progression going forward. Let's begin with the OASIS problem statement. In the Artemis program's efforts to return to the moon by 2024, water will be a vital resource. Water is needed not only for astronaut hydration, but also for sanitation, agriculture, life support systems, and even manufacturing. Previous NASA missions, including LRO and SOFIA, shown here, have detected water in PSRs, or regions on the moon that never see sunlight. These high-density areas are extremely promising since mining for water in situ is projected to be significantly cheaper than transporting it from Earth. Water is scattered throughout PSRs in non-uniform patches, as shown by this mapping of LRO data onto the lunar surface. Thus, data on the specific location and concentrations of water within these regions is needed to mine them cost-effectively. As part of the 2020 NASA Big Data Challenge, SSPL is developing OASIS, a laser-induced breakdown spectroscopy instrument designed to provide detailed, locally procured data on the concentration of water within PSRs, directing the Artemis program towards areas where their water mining efforts will have the highest return on investment.
Hello, my name is Drew McConnell, and I'm the Science Subsystem Lead for OASIS. Laser-induced breakdown spectroscopy is a chemical analysis technique in which a pulsed laser is focused onto a sample, creating a plasma. As this plasma cools, characteristic wavelengths are emitted from elements in the sample, and this light is captured by collection optics, which funnels the plasma light into a spectrometer for spectral analysis. The expanding plasma that is induced at the point of ablation is very sensitive to ambient pressures, making LIBS more difficult. As shown in this image, at low pressures the plasma expands rapidly, resulting in the intensity recorded by the spectrometer to be lower in near-vacuum environments like the moon. This means that the LIBS system will have to be more precise. The emission spectra of elements and compounds in ice water, along with elements frequently found in lunar regolith, cover a wide range, from around 250 nanometers up to almost 800 nanometers, with the most important for the detection of water being hydroxide at 306 nanometers and hydrogen at 656 nanometers. As a result, OASIS must be sensitive to a wide band of wavelengths.
Let's begin the description of the OASIS project. To reiterate, OASIS is a LIBS instrument surveying the moon's surface for water. The OASIS design adheres to constraints outlined specifically by the 2020 NASA Big Idea Challenge, as shown in the table below. A quick note, while there was no volumetric requirements outlined by the competition, we felt it appropriate to list these figures alongside the mass of the payload. To manage the scope of the project, the following assumptions were made throughout design. Number 1, as per the competition constraints, OASIS assumes adiabatic mounting to its host vehicle, or minimal heat transfer. Second, the temperatures in the lunar PSR are assumed to be between 20 and 40 Kelvin. Lastly, OASIS assumes that during launch, flight, and descent, it will either be A, stored within operable temperatures, or B, provided the power necessary to manage its own temperatures by the host craft. Lastly, before we discuss the design of OASIS, let's talk about the context in which this design was developed. Due to COVID-19 safety regulations, OASIS was developed almost entirely remotely. Tools like Microsoft Teams, GitHub, and Zoom were utilized to facilitate work between team members from across the country. To ensure student safety, Penn State shut down almost all research in March, which included testing facilities. For the roughly 5 months that followed, SSPL had no lab access and no knowledge of when or whether it would be restored. With the limited access that SSPL did get in August, no more than 2 members of the lab were allowed in the building at once, and no campus testing facilities were open. To account for this, analysis and simulation was used to verify design decisions where physical testing was not possible. Fortunately, the Naval Research Lab, or NRL, allowed for the physical assembly and testing of the OASIS LIBS system in early October. The OASIS team gained valuable insight from these tests, and the results of them are discussed in detail in the proof of concept testing and verification section. The OASIS team is extremely grateful to NRL for their help with testing. Now for a summary of the OASIS system design. Shown here is the OASIS system block diagram. I've moved my window to the upper right so as to not occlude it. Starting from the top left, we have the power system, which takes the 28 volts direct current signal from the host craft and converts it to the appropriate component voltages. Second, we have the BeagleBone Black Industrial flight computer, which controls the laser and spectrometer used for LIBS, and the thermal control system used to regulate the temperature of payload components. Lastly, an RS-422 line driver and 2-port USB hub allow the flight computer to communicate with the host craft and the instrumentation in the appropriate communication protocols respectively. Shown here is a top-down view of the OASIS payload without the lid to give a clearer picture of component layout. Starting at the top, we have the spectrometer and laser driver, connected to their respective optical systems through fiber optic cable and laser head. The spectrometer telescope is intentionally angled inwards towards the focusing optics for reasons to be discussed in the science and optics section. Lastly, the power system and flight computer are mounted to the housing beneath the fiber optic cable to save space within the payload.
Now I will be talking about the science subsystem design. To successfully perform LIBS, the laser must meet a required power density of 5 gigawatts per centimeter squared at the point of ablation to fully ablate the lunar regolith. Additionally, the spectrometer resolution must be accurate enough to detect individual elements. OASIS uses the Quantum Composer's microjoule, a diode-pumped solid-state Nd:YAG laser, which is shown above. Its small size and low power consumption, along with a large pulse energy of 11 millijoules and short pulse width of 4 nanoseconds, makes it well suited for a compact LIBS system like OASIS. However, this laser is not powerful enough to ablate regoliths without the use of focusing optics. One quick side note is that the heatsink on the laser head is different from the one used on OASIS, and the correct one will be shown on the next slide. To focus the laser, a beam expander and a focusing lens, both V-coded for a 1064 nanometer laser, are used. The 10 times beam expander increases the diameter of the beam as it enters the focusing lens, allowing for a smaller beam diameter, resulting in a larger power density at the point of ablation. To focus the laser, a 300mm focal length plano-convex lens is used. Furthermore, the shutter shown here is only a safety precaution used during testing and is not part of the focusing optics system. The collection optics consists of a series of 4 lenses, a 2-inch objective, 1-inch plano-concave lens, 1-inch plano-convex lens, and a collimating lens. The 2-inch objective was chosen to maximize the plasma light captured by the system, because the more light that enters a spectrometer, the more distinct each peak will be. Also, the pair of 1-inch diameter lenses will collimate the light to allow for a 1064 nanometer filter to block the laser light from entering the spectrometer. After preliminary testing, it was found that even slight misalignment of the collection optics with a source of light will result in the collection of significant background noise. Therefore, the telescope needs to be directly aligned with the point of ablation. To facilitate this, the collection optics were turned rather than the laser focusing optics, because the fiber optic cable can be bent, as shown in the image above, resulting in only minor changes to the housing. To analyze the captured plasma light, OASIS uses a Flame-T UV-Vis spectrometer by Ocean Insight. The Flame-T has an optical resolution of 1.33 nanometers, allowing for the ability to accurately distinguish between emission lines of different elements. Additionally, the Flame-T covers a wide range of wavelengths, from 200 nanometers to 850 nanometers, allowing for detection of water along with other metals commonly found in lunar regolith. After preliminary testing, which will be discussed later in the presentation, it was found that improvements can be made to the science subsystem, such as the use of a spectrometer with a faster integration time, like the Ocean FX, to minimize the collection of background noise, and the need for a custom 1064 nanometer notch filter, which will easily integrate into the current optical design.
In the following section, we will discuss the structural design for OASIS. The OASIS housing consists of a 32 cm by 21 cm by 10 cm box of 6061 T6 aluminum with half centimeter thick walls. There are 2 3 cm wide flanges on the side with 3 evenly spaced mounting holes to secure the housing to the host vehicle. Additionally, there are 3 evenly spaced screws on each side wall to secure the lid. The OASIS housing will be made of 6061 T6 aluminum, which has multiple advantages over other alloys. 6061 has extensive flight heritage, suitable thermal properties, and structural integrity, while also being accessible and lightweight. Aluminum standoffs are used to secure the components in place. Larger components, like the laser driver, spectrometer, optical system, and beam expander, are held into place by brackets and standoffs. The laser driver and spectrometer also have base plates, since they do not have built-in standoff screw holes. To minimize the Oasis housing footprint, we chose to keep the standoffs for the components at differing heights. This allows us to layer our components and have the fiber optic cable and laser placed over the PCB. Minimizing the payload footprint allows Oasis to be operated within a suite of instruments on various host platforms. We took the requirements of the Science subsystem and designed a custom bracket such that the optical system is pointed directly at the point of ablation, yielding the highest quality data. To facilitate manufacturing, the bracket is a separate piece that inserts into the housing wall. By having the angled hole cut into the separate bracket piece instead of being integrated into the housing, the cost of manufacturing is decreased. Without the use of this bracket, a 5-axis mill would be needed to cut the hole at the angle required, which would make the manufacturing process more difficult. When designing the Oasis payload, manufacturability was heavily emphasized. Following the DFM guidelines of faculty advisors, any interior corners found in the housing have been rounded to reduce milling cost. By rounding the inside corners, the housing is easier to machine. The standoffs are separate pieces and are screwed into the tap-through holes found in the bottom of the housing, rather than being milled as one piece. This way, less material is wasted when machining. In continued path-to-flight development, any new changes will be implemented using the same DFM process to ensure that manufacturing cost and complexity will be minimized. As part of the path-to-flight process, vibrational analysis and simulations will be conducted to identify necessary design changes. Once these changes are implemented, a shake table test will be conducted to verify the structural integrity of the housing and its components. As part of the design changes based on vibrational analysis, a support structure will be added to the fiber optic cable to prevent any potentially harmful oscillations.
Hello, my name is Sam Lunger, and I am one of the thermal subsystem co-leads. Today I am here to talk about the design of the thermal control system for the Oasis payload. The thermal control system for Oasis includes both active and passive heating. This thermal control system was designed under the assumption that the temperature of the PSR will be 20 Kelvin, to ensure operational temperatures are met even in the coldest conditions. For the passive heating aspect of the thermal control system, Oasis will use a polished aluminum exterior finish with a target emissivity of 0.0425 to reduce heat loss to the environment. Reducing the emissivity of the outer aluminum surface of the payload allows less heat to escape to the exterior environment. This specific target emissivity was determined through analysis in COMSOL multiphysics, which will be explained in greater detail in the testing section. Polished aluminum was chosen as the surface finish because it is a relatively inexpensive and simple process to implement, compared to other options, while still providing the desired emissivity. For the active heating system, 6 2-inch by 2-inch polyimide heaters, controlled by a PI loop, will be used to regulate the temperature of components. The attached pressure-sensitive adhesive will be used to attach them to their respective surfaces. 2 heaters each will be used for the laser driver, spectrometer, and PCB to provide redundancy in case one debonds or malfunctions.
In order to keep the payload at an operable temperature, Oasis uses a smaller microcontroller, known as the thermal logic controller, to determine the amount of heat that is delivered through the heaters. The thermal logic controller is a smaller powered device, so it doesn't have enough power to drive the heaters alone. Instead, we amplify the PWM signal from the thermal logic controller through N MOSFETs, which amplify the signal up to 28 volts, which is enough to power the heaters. You'll quickly notice, however, that this is a feedback loop between the generated PWM signal to the amount of heat dissipated by the heaters to the temperature measured by our thermistors. To control this feedback loop, the thermal logic controller is programmed with a proportional integral control system with anti-windup. The thermal logic controller is actually programmed as a PID controller, however, we have set the derivative coefficient to 0. We made the decision to set this derivative coefficient to 0 because our system does not need rapid response to changes in temperature, and also because it makes it simpler to find the remaining 2 coefficients. Although we could find these 2 coefficients through simulation and analytical methods, in a path-to-flight scenario, Oasis would have to be placed in a vacuum chamber that can reach temperatures comparable to that of a lunar permanently shaded region in order to tune these coefficients. Additionally, the thermal logic controller is programmed with anti-windup to prevent the integral term from being saturated when changing the target temperature, such as going from an operational state to a standby state where a lower target temperature is allowed. Overall, the thermal logic controller and active heating elements will be able to keep Oasis at an operable temperature while in a lunar permanently shaded environment.
In the electronic subsystem, we will first discuss the flight computer code, followed by the hardware design that provide power and telemetry to Oasis's submodules.
To develop the flight computer code for OASIS, we followed the state machine diagram shown on screen. The state diagram was used to plan out our software's commands to control the various components of OASIS. The left side of the diagram showcases the commands we use to change the states of the laser. Based on this, we created a laser library to interface and control the laser with our flight computer. We also developed libraries to simulate laser actions to rigorously unit test our laser library in flight computer operations. Now to the right side of the diagram, this showcases the commands we use to change the states of the spectrometer. For this, we use an open source library, Seabreeze, to control the spectrometer.
The OASIS PCB provides the hardware required for power delivery and communications for the laser, spectrometer, and thermal control system. As shown in this power draw diagram, 28-volt DC is passed to two DC-DC converters and the heater control MOSFETs. A 48-volt converter supplies power to the OASIS laser. A 5-volt converter supplies power to two 3.3-volt regulators, the BeagleBone Black flight computer, and the spectrometer. One 3.3-volt regulator is the dedicated power supply for the Teensy 3.2 thermal logic controller, while the other supplies power to the USB hub and RS-422 line driver. The two power states represent total power draw during system standby and during laser activation. OASIS conforms to the power constraints laid out by the Big Idea Challenge as shown in this power draw breakdown. The payload will maintain a continuous power draw of 5.19 watts and an operational power draw of 28.69 watts for less than 5 minutes while the laser is activated. Variations in total power draw arise from the possible power draw of the heating system, but will never be reached in practice due to the payload's thermal design.
In summary, various versions of the hardware and software interfaces are iteratively designed and implemented to verify adequate power and telemetry for OASIS. To ensure robustness and safety, a command line version of this code was also developed for actual laser fire and testing. In a path-to-flight scenario, our electronic components will be replaced with radiation-tolerant versions. For example, we plan to replace our flight computer, a BeagleBone Black, with a radiation-tolerant version developed by Pumpkin Space. We will also utilize a real-time operating system such as RT Linux to ensure guaranteed response time with the rover. Data error checking code and single event latch-up recovery procedure will also be implemented to guarantee system and data integrity.
We will now discuss the major changes since the proposal. Our initial design involved 3 thermally isolated chambers, each kept at their own temperature to theoretically limit our total power consumption. However, further analysis revealed that by combining our components into one single smaller chamber, we are able to reduce the total surface area of the payload enough that the payload radiated less heat and thereby consumed less power. This final design also allowed us to significantly reduce the size and weight of the payload. Structurally, we moved from standoffs, pictured on the left, to the phalanges, pictured on the right. To best moderate the heat moving in and out of our payload through radiation, we initially planned to use multi-layered insulation, or MLI. However, our computer model showed that this MLI had an effective emissivity that was too low, and resulted in less power leaving the system than needed. This could result in overheating of the system. This problem was alleviated by instead choosing to focus on manipulating the surface optical properties of the aluminum housing. This was done through polishing and would allow us to achieve our target emissivity while also cutting the cost, size, and weight associated with using MLI. Our optical system also underwent several changes throughout our design, the first of which being a larger objective lens was used in the spectrometer telescope. This telescope is also oriented slightly to better align with the point of ablation. This telescope is then connected to the spectrometer via a fiber optic cable. Finally, focusing optics were used on our laser system to achieve our target power density to fully ablate the lunar regolith at our point of ablation. Our final change was using the BeagleBone Black Industrial as opposed to the proposed ISIS onboard flight computer. This decision was made in part due to the long lead times on delivery of the ISIS as opposed to the much more readily available BeagleBone. This allowed us to move more early into the prototyping phase during our development. While the BeagleBone is somewhat less robust than the ISIS, it still has a history of space heritage and allowed us to fully test our code and computer functionality.
We will now discuss proof of concept testing to verify our previously discussed designs. We will begin our discussion with the laser-induced breakdown spectroscopy system testing, which we were very fortunate to be able to accomplish at the Naval Research Laboratory facility despite COVID restrictions. This test successfully verified the spectrometer laser interface software for the flight computer meaning that the flight computer, our BeagleBone Black Industrial, can successfully command and receive data from the spectrometer and laser. The laser beam expander and spectrometer telescopes were also integrated into the laser and spectrometer respectively during this test. Finally, our thermal team gained valuable insight on the heat output of the laser diode when it fires. This is us firing the laser at 5 Hz, as we can see in this video. So this footage, along with telemetry, verified that the laser system, including the laser beam expander, the laser itself, the laser command box, our custom-built laser interface library in our flight code, as well as our command line control of our system by an operator, the spectrometer sample interface, and data handling for both real-time response and data storage capabilities were verified in this test. Ultimately, as we can see in the video footage from the test, confirmed that OASIS can successfully ablate lunar regolith simulant. So the actual test was conducted inside a black box, so the spectrometer is sampling and alighting similar to the lunar PSR. Still, the sample data indicated significant noise in the spectrometer's readings. Based on the data and further testing, many solutions have been proposed and are implemented to solve this issue. The OASIS optics system has demonstrated sensitivity to misalignments. Therefore, it is possible that the optics system was misaligned during testing. Mounting the lib system to the payload housing will ensure proper alignment going forward. Using an external trigger will also decrease the lag time between laser fire and spectrometer sample. This will allow for a shorter integration time, reducing background noise. Implementation of an external hardware trigger has already begun. Finally, test data indicates that it is possible to sample more frequently than anticipated by the OASIS team without overheating the system. Collecting many samples will allow for the averaging out of the initial electric noise.
In order to test our active heating circuitry, we assembled a smaller prototype board that contained only one MOSFET and one polyimide heater. To the left, you can see the circuit schematic that contains all the parts needed to control one of these heaters. In the center, you can see the circuit fully assembled for testing, and to the right, you can see the oscilloscope output for the voltage on the MOSFET gate relative to ground. You can see that it has a nice sharp rise and a nice sharp decline. Based upon this test, we're able to verify that yes, we can control the amount of power delivered to the heaters by varying the duty cycle of the PWM signal coming from the thermal logic controller.
Now on to spectrometer thermal stability testing. A thermal stability test was performed on the spectrometer to verify the temperature fluctuations during operation will not cause significant shift in the wavelengths recorded by the spectrometer. As shown in the graph on the left, shorter wavelengths experience a larger shift with temperature change. However, even the shortest wavelength only experiences a 0.89 nanometer shift after a temperature change of 20 degrees Celsius, which is below the 1.33 nanometer resolution of the spectrometer. Therefore, during sampling, spectrometer data will not be impacted by temperature drifts.
Now I am here to talk about the thermal simulations used to verify the thermal control system for OASIS. A thermal model of the payload was made in COMSOL Multiphysics to simulate the components in a PSR environment. All of the components were modeled with their approximate dimensions and physical properties through COMSOL's built-in geometry tool. This simulation was used both for determining the most desirable emissivity for the passive heating system and to verify that components could be regulated to an operational temperature in a PSR environment while still using under the 3.3 watts of allotted power for the heaters. The outer emissivity of the payload and the heater output were varied to see the effect on the temperature of the components. A target emissivity of 0.0425 was chosen because at this emissivity, the required heater output was well below the 3.3 watt max, and components were successfully kept within 1% of their target temperature. It is known that the emissivity from polishing aluminum is between 0.04 and 0.051. The target emissivity for the payload of 0.0425 is within this range, but it is unlikely that polishing the aluminum will produce this exact value. As shown by the above graph, the required emissivity for the housing is directly proportional to the heater power needed to maintain operational temperatures. This means that with some variation in the emissivity of the polished aluminum, adjustments in heater power will successfully maintain operational temperatures.
We will now discuss the path-to-flight testing. A thermal vacuum test will be performed to assess the basic functionality of the thermal system, independent of other components. This will be done in a simulated lunar environment, which involves low temperatures and negligible atmosphere. The Navy Research Lab is one possible location for this test, but could also be done at other facilities, such as the NEST facility pictured here, for example. The test will involve slowly cooling the payload to a temperature of around 40 Kelvin. Once it has achieved this low temperature steady state, we will be able to test and tune the PI coefficients that make up our thermal logic controller. We will also be able to gather data on the speed at which warming and cooling can occur. Finally, we will simulate laser fire to test the heat dissipation of our payload.
As part of the path to flight process, a shake table test will be conducted as verification that the OASIS design will be able to withstand the forces experienced at launch. Based on the results of these tests, design changes will be implemented as necessary.
If given path to flight, OASIS will also perform an integrated system test in a cryogenic thermal vacuum chamber in which ablation can take place, such as Vacuum Facility 13 at NASA Glenn. The integrated test will assess the ability of OASIS to perform LIBS in a simulated lunar environment, while also testing that the thermal control system can maintain operable temperatures inside the payload. During testing, the payload will be placed in the chamber and the pressure will be dropped. Then the temperature will be lowered incrementally to ensure that sensitive components in the system are not damaged in the event of a failure of the thermal system. This will test that the heaters and the coating can maintain the target temperature inside the payload, and it also ensures that the PI coefficients have been calculated correctly so the thermal logic controller can properly regulate the temperature inside the housing. While a LIBS test was performed, this was in a laboratory environment rather than a simulated lunar environment. As explained in the background, the low pressure on the moon changes how the plasma expands, resulting in a difference in the data that is collected. Once both the temperature and pressure of the chamber have reached their minimum, LIBS will be performed, verifying that OASIS can perform LIBS in a lunar environment.
In conclusion, the OASIS instrument has made significant progress since its proposal in the fall of 2019. The laser and spectrometer optical systems has been designed, assembled, and verified through preliminary LIBS testing, in which lunar regolith was successfully ablated. Also, the structural design of OASIS has increased in resolution significantly, with payload components organized in a way such that they minimize the footprint of OASIS, allowing it to be operated within a suite of instruments on various host platforms. Both the active and passive thermal control systems have been verified through analysis, testing, and simulations. Testing and simulation work indicates that the payload is able to maintain operable component temperatures during standby and firing states, and that spectrometer readings are negligibly affected by expected temperature variance. OASIS software has been written and tested extensively, resulting in its successful use during the preliminary LIBS test. This software gives the flight computer full and reliable control of the laser and spectrometer, and the ability to transmit data to and receive commands from an external source. The increase in TRL from 2 to between 3 and 4, despite COVID-19 related challenges, is a promising start to a potential path to flight for OASIS. Thank you for your time.